Again, A and B carried forward. Here what you'll notice I've done is I took A here, I added in the B there, which ends up subtracting that there. Keep going, and what you'll see is this expression that says mu t plus, our new belief after we've taken our measurement, is just mu t minus. What's mu t minus? Mu t minus was the prediction. And then we have to change that prediction a little bit. And that prediction is changed based upon two things. The first thing is based upon this difference here. What's that difference? That difference is the residual, right? Y divided by m, that's the measurement's guess, right? That's the measurement's guess of x. Mu t minus was your prediction. The difference between them is the residual. And I multiply that by some factor k. And that k is called the Kalman gain. If my Kalman gain was 0, then I ignore my measurements altogether and I just go with my prediction. Okay? If my Kalman gain was 1, let's see, I put mu t minus mu, I ignore my predictions altogether and I just get my measurement. And it's that Kalman gain that you're estimating that goes between essentially 0 to 1 in the scalar case and does something funkier in the multidimensional case. All right, let me show you that in a simple example. And this is going to be a constant velocity model. And what we mean by that is we assume that the velocity is constant except a little bit of noise. So the state is two-dimensional. It's the position and the velocity, right? So it's I'm moving in one dimension, but my state is two-dimensional because it's the position and the velocity. And now we're going to take a look at this graph, all right? So in this graph, all right, so we have time and position as the things we're measuring and the thing we're estimating. The red line here is the state. This, we happen to know, was the actual underlying state, okay? How did we know this? We booked a trip to Delphi. You know where Delphi is? It's in Greece. They have a thing there called the Oracle. They also sell really good baklava, but that's besides the point. You go to the Oracle, and the Oracle tells you the truth, okay? It tells you whether the Mets will win the World Series. They always say no. And they also tell you the state. But the idea is, for the point here, I'm just showing you the graph. That's the actual state. But we also took some measurements, okay? And the green dashed line, these are the measurements we happen to get. Now, you'll notice pretty crummy measurements, right? Life is the way life is. This is the noise that we actually happen to get. The purple line here is the corrected mean, okay? And what you're seeing here is that the mean is sort of being pulled around, the estimate, all right, is being pulled around by the measurements, but you see that it tracks the real state much better than the measurements do, right? Because it's blending a prediction where it's estimating the velocity with the ability to incorporate the measurements. If you want to take a look at the error bars here a little bit, one of the things that's cool, in fact, I'll look at just the last one, right? This was the error bar of our prediction. Okay, so remember, see it says the predicted mean, which is right there. And then after we did the Kalman filtering, this was our new guess, all right? And our error bars got smaller, okay? So again, this is what's happening is we take a step, we get bigger, we take a measurement, we move, and we get smaller. What I just showed you were the formula for the one-dimensional case. We almost always do this in the n-dimensional, because even when we were having x move in just one direction, we had a two-dimensional vector of position and velocity. In the two-dimensional case, these are the Kalman equations, okay? We have our state vector x. We assume our prediction is just based upon a linear transformation. Our covariance prediction, or the covariance of the prediction, this is that squaring operator. Remember before we did d squared sigma? Well, when you're doing this in matrices, it's d times the old sigma times d transpose. That's the squaring. Plus you add in the noise, the process noise. So those are your prediction measurements. And then your correction looks like the things on the right. The thing for you to notice here is, you see the quantity in the green box? This is the residual right there. And you're multiplying it by this Kalman gain matrix, all right? And the Kalman gain matrix has less weight on the residual as the prior covariance estimate approaches 0. So as this values it's hard to say what it means for covariance to go to 0, but let's talk about its trace. But the idea is that it's getting smaller. As it gets smaller, the Kalman gain goes down, which is what you want to have happen, right? If your covariance of your prediction is very tight, I don't want to pay a lot of attention to my measurement, so I don't want to weight the residuals very much. On the other hand, if my measurement covariance goes down, okay, so now what happens is this value is very small, which means this value is what's getting put in the inverse, right? So now this sigma t goes away. What happens is the Kalman gain matrix goes up, its magnitude, if you will, goes up, and it weights the measurements more. So these matrix equations are doing exactly the same thing as the scalar equation did of balancing the prediction and the measurement. There's a really nice little graphical illustration of tracking with Kalman filters. So let's suppose we have some current estimate of where we think things are, right? And that's what's represented by this little circle here in the xy plane. Our prediction shifts and grows, and that's why the size, if you will, and you can think of this as being a single, say, some number of standard deviations of uncertainty. So our uncertainty matrix got significantly bigger, and the mean may have shifted as well as also, so that's our prediction. We then take a measurement, and you'll notice that the measurement here is offset a little bit. I mean, it happens, you know, its mean is right in the middle, and it's actually tighter. So it actually has a tighter covariance than the prediction, okay? But the thing that's important to realize is the correction has a tighter covariance than either one of them. So you'll see that the mean of the final correction is somewhere between the mean of the measurement and the mean of the prediction. Remember, it's going to be a weighting between them. And also notice that the covariance of the final corrected estimate is smaller than either of the two, all right? And this might seem a little weird when you look just at, say, the covariance of the measurement and the covariance of the prediction, because they're both pretty big. And you might ask, how is it that the covariance goes down even tighter than the measurement? And again, the answer is information can only reduce your uncertainty. So whether you think of as measurement as reducing your uncertainty about the prediction, or the prediction is reducing the uncertainty about the measurement, what that means is your final covariance will be less. You'd be amazed at the number of PhD qualifying students who, when asked that question standing in front of the board, kind of flump through it. So if you're thinking about doing a PhD, and I'm going to be on your qualifying committee, and you're doing something in robotics, get to know and love your Kalman filters. This can be seen sort of simply in this 1D case. So we start off with a prior, and here it is as a Gaussian. We have some measurement, that's the evidence, and here it happens to be tighter. And then we get a posterior, right? And the posterior is narrower, and because it's narrower, it's also going to be taller. And then the prediction step, we just take that posterior, and we do the shift, and we grow the uncertainty again. So far, everything looks like it's behaving really well. So let me give you a quiz. Well, it's not a real quiz. It's like a fake quiz, all right? Suppose this is your prior, okay? Okay, so you see it's this nice white Gaussian lump over here. And then suppose this is your measurement, okay, this nice tight green. Where does the posterior go? Well, first of all, it's got to go somewhere in between, because in Kalman filtering, your mean is a weighted average between the prior's mean and the measurement, okay? So the fact that it's going to go in the middle is okay. But what might bug you is it's got, again, that tight little uncertainty. I got this Gaussian bump here, all right? Now, Gaussians go to 0 really, really fast. So by the time we get out here, it's like incredibly unlikely. But then all of a sudden there's a measurement bump over here, okay? So, you know, what's poor Kalman to do? Well, Kalman has to put them somewhere in the middle because that's all it does. And furthermore, it has to reduce that uncertainty because it's a slave to its model. It really, honest to God, believes that things are distributed by these Gaussians. And if they really were, then that's the correct value to put in. And the question is, does this agree with your intuition? And the short answer should be, I don't think so. Because, Megan, over here, okay? If I've really got a Gaussian lump over here, then the idea that something will now be over here, the probability is so infinitesimally small that what's probably the problem is that our model is wrong. We really should be trying to abandon the model at that point as opposed to doing the integration. And in some sense, that's the part of the message of Kalman filter. You're actually a slave to the model. You really believe it. So reviewing it, sort of the pros and cons. What's the biggest pro of a Kalman filter? It's all listed here as one, but look, it's just very simple. You know those equations, you just implement them, you write them, it's compact, it's efficient, it works pretty well. You have to sometimes tune some things, like you never want to let your process noise get too small. It's much better to overestimate process noise than under. Why? Because if you, for example, suppose you didn't think there was any process noise at all. You thought this point is just there, okay? So you're taking measurements. Well, if there's no process noise, remember, every time you take a measurement, your uncertainty goes down. Eventually, you'll go to an uncertainty of 0, and you'll stop listening to your measurements. So it's always good to have a little bit of process noise. So there's some tuning to make it work, but in general, it's pretty clean. The biggest problems with it are that it's, first of all, fundamentally a unimodal distribution, right? I've basically got a Gaussian, which means I basically have a single hypothesis, right? And it's some uncertainty within that hypothesis. There are some other issues here. Remember, we have this linear model. There are ways of fixing that. There's something called the extended Kalman filter, which basically just takes, for those of you who care, you linearize about your current point. That's like taking a Jacobian around a nonlinear system. You currently estimate it linearly, update, then recompute your equations in the nonlinear prediction. So the linearity part is not that big of a problem. But this problem of having a single hypothesis, okay, that's a Gaussian, that doesn't work so well sometimes. So the question is, what should you do if the world's not Gaussian or it's not even unimodal? And the answer is, you should come back next time, because we'll tell you then. Welcome back to Computer Vision. Today we're going to continue on our long and winding excursion through tracking. And in particular, what we're going to do today is we're going to revisit the whole notion of Bayes-based filter tracking or Bayesian tracking. And sort of develop a method that allows us to do that well. So you remember the tracking with dynamics, right? So the whole idea was, because we're tracking something that's moving with respect to the imagery, we're going to learn something about the dynamics and use the dynamics in order to make predictions. And we're doing this so that we can limit the area of search that we're looking in, and also so that we can get a better total estimate when we're done, under the assumption that the things we were trying to track, you can't perfectly detect them and it's noisy to begin with. And we're basically making an assumption that there's some sort of smooth motion going on, and that essentially our dynamics don't surprise us is the underlying element. So last time we developed what was called the Kalman filter. And the Kalman filter was for linear dynamic systems, where you had Gaussian noise context. So what we meant by that was the motion could be predicted by a linear factor applied to the motion that you've estimated, and then you add in some Gaussian noise if you were thinking about what the uncertainties are. Same thing with our measurements. They were a linear function of the state, and then there was some noise. And what was nice about it is everything, prediction, correction, your lunch break, it's all Gaussian. All right? And so the only thing you have to do is maintain the mean and the covariances of these Gaussians. And it just works in 1D or ND, et cetera. It's real easy. And the calculations are pretty straightforward also. I mean, the equations look a little ugly, but it's just a bunch of matrix multiplies and a couple of inverses. Pictorially, the Kalman filter looks like this. Nice Gaussian. I don't know why I'm drawing this. It's already here. A Gaussian. I'll circle it. We start off with that Gaussian. We then have the linear prediction part, which does the shift. We then say, but wait a minute, there may be some noise, so things get widened. We take our measurement and we sort of blend. Remember, it was that the Kalman filter is a blending between your prediction, which is what our prediction here was, and your measurement, and it creates a new estimate that's a weighted average between those, depending upon the relative uncertainties. And the uncertainty gets smaller after we take the measurement. So uncertainty gets bigger when we do our prediction because we don't know exactly what happened, and then it gets smaller again when we take the measurement.